Okay, good afternoon, everybody. My name is Tobechukwu Onyema, and you can call me Tobe. I'm a product engineer and architect. I solve problems basically by enabling people and technology, and I currently do that as an engineering manager at Core. I've been an engineer for about 5 plus years, largely in the finance space. Building and designing systems and products is something I enjoy doing a lot. And when I'm not doing all this geeky stuff, I spend a lot of time trying to beat my personal records at the gym. So yeah, so you see me doing stuff like this. I would advise you not to try at home, anyways. Um, so yeah, coincidentally, while I was making this presentation, I realized that like the title sort of starts off like an acronym for gym, and I was like, wow, this is written in the stars, I guess. Um, yeah. So just diving into why we are here. This is basically around the talk today is basically around like security, and I have like three main objectives with this talk. And first of all, to sort of simplify how we understand like go about security, like a framework for thinking about it, and to talk on securing like sensitive data, and particularly like card pins and how it's done in core where I work, and sort of build your trust in the systems that actually power your day-to-day transactions. So give you an understanding of how it works so you can better trust like the things that back them up. Um, so this basically from table of contents. I'll be talking a lot basically about how I walk through thinking about security, especially as someone who is a lead, right? And you trying to build up something new. And even if you may not have like some deep understanding or some certification, you can still be able to build a system that's secure. Um, and then talk on how this particular thing is applied into pin security, usually like card pin security being the context, and discuss briefly on the concept of like defense in depth, and how it sort of like pertains to you as an engineer, basically, or a business owner. So thinking secure, right? I like to. I don't know if a couple of us may not have heard this term "follow the money." Most likely in some investigative movie or series or something like that. And this is just basically saying like if you want to discover what the truth is about any, um, like maybe criminal activity or something, like you just need to follow the thing of value that people are trying to find. Um, and yeah, that will sort of give you insight into you know the places that could be compromised. And in financial space, right, our data is equivalent to money, literally, right? There's a lot of digital transactions like has nothing to do with cash, to be honest, and everything to do with records of information and keeping up ledgers, right? I don't want to go deep into the accounting of that, but that's basically what it is. And so yeah, we're going to be following the data, and this is sort of like the concept I approach in order to navigate whether my system is secure when I'm trying to build any new system, is to follow the data so I can understand how to safely guard the data, right? Um, yes, so this is bringing into uncomfortable scenarios, right? That as a lead, like you might come across. I hope you don't come across the latter one. But first one is a downtime, right? Those someone calling you randomly at Sunday to tell you that something is down. It gives you a sense of like there's some certain tension you get from that. But having that kind of case as a result of a security breach is a lot more unnerving and scary than um, if you had a downtime that's something within your control. Once security has been breached, right, it becomes a lot more scary because then you may be facing some legal repercussions, right? And this was something I had to understand, right, when I became a lead, and it was very unnerving to me. So like, okay, how can I make it easier for people to be able to do that on their own, right? So yeah, so that's why it's talking about security as a talk. So security basically is like access management, right? Who are you trying to access? Who has access to what? That's basically what it's about. And in our case, it's data, right? Hence why I'm saying follow the data, and that's sort of where we are starting from. In order to think secure, there are certain steps I sort of go through to be able to understand or access whether my system as a whole is secure enough to be able to handle this particular type of data. And it starts with classifying my data, what exactly is my data, and putting them into relevant groups, mapping this data into like trying to figure out the path of this data, where is it moving from, and how is it being transformed along the way. Um, Sort of like pinpointing what the requirements is for or the security objectives for that particular piece of data, and then picking something appropriate to guard or secure that data, right? and then I review and repeat periodically every 6 months. And this is the same thing we apply also in like practically, right? So once you understand data within your context, and just to note, I know we're speaking on digital, I'm speaking on digital transactions or digital, maybe digital transactions here, but I think this also applies to physical things, right? If you're trying to secure money in your house or whatnot, right, is understand what it is data within your context, and then you start sort of like try to define what sensitive means, because sensitive data and these are the kind of data that actually compromise your system if exposed. So you have to sort of identify what that is, and then to what degree is this sensitive, because that tells you how much priority you should put into like guarding these things, right? And then we have different levels: low, medium, high, extremely high. Extremely high most likely would have you into land into some regulation problems. That's really detrimental to businesses, could lead to fines, sometimes could revoking licenses and stuff like that. So once you've been able to classify data, then you sort of walk through how it is being transformed, and you think about it in three states: like when is it at rest, when is my data in transit, and when is my data in use. Popular places to think to look to will be the databases at rest, storage devices, digital media like screenshots, videos, backup files, your logs, and code. Like I've seen this overlooked a couple times, simply because it's internal. And then you have things like when it's in transit over a network. This is most likely the ones people secure the most. And then you have when it's in use, like within in your application memory, for instance. Once you be able to understand those three states data in, and you can map each data to when they are in those three states, then you sort of assess what the requirements are. And a good place to start is understanding what the standards are for your industry, whatever the industry is, and also the assessing risk of this being breached. And that sort of gives you a sense of how you should navigate security for that. And once you've been able to do that, right, then you start to pick certain techniques. Now, this isn't exhaustive, right? I just selected certain things that apply to like PIN today. And we have things like encryption, which is you get a text, pass it to algorithm, pass a key, gives you a ciphertext. You can decrypt that ciphertext with the same key. Tokenization is sort of mapping like values to some random, something random, right? And that generates like a very useless like piece of string that you actually have can't use to do anything. An example would be if you went to park your car and they give you a ticket to say, okay, this represents where you parked your car. You can't drive with the ticket, but you can drive with your car. So that's an example of tokenization. And then you have data masking. Data masking is something like what you see when you hide a balance on your phone, where you see XXXXX over it, right? That's called dynamic data masking, anyways. Um, and yeah, so then integrity of your data, you have things like digital signatures that sort of make your data tamper proof, such that like if you move it from one place to another, the person, the destination sort of knows if when this stuff was sent in the first place, it's still the same thing that it received at the end. And every single thing here is built on top of checksums, to be fair. Um, yeah, and then you have things like availability. So when it comes to things like privacy, like it's very good to have retention policies in place to sort of invalidate certain data after a period of time when you do not need it anymore. Because the longer you keep stuff that you shouldn't have, the more likely it is for you to breach it at some point. Yeah, and now we'll now go into how this is done in at core. I think is the premise is first to understand what I do at core. Core is a financial services, like a tech company, a fintech company, basically. What we do basically is we sort of automate financial services, right? And we're like at an infrastructure level. So we provide things like core banking systems to banks. But the system that I work with, we provide agency banking solutions and merchant payments to banks, and they in turn provide it to their customers. So when you go to POS to withdraw money, right? The things that power that's sort of what I do, right? So so we're going to sort of walk through how this was applied to understand the techniques we used in securing pins. Spoiler alert, I love spoilers, by the way. Um, is encryption. That's the end goal. Like this is what we chose in the end. All right, we chose encryption. And to sort of understand like why we choose encryption. So like you mentioned, like payment services, like division I work in, we are licensed to handle card data. Not everyone is licensed to do that. And we're licensed to be able to route this to different payment processors like Zone Switch, which is our sister company. nibs into switch likes, right? And they in turn route it to your issuing bank. Issuing bank is basically the bank that give you your card. And yeah, and we have to be compliant, and we are regularly audited. So it's quite very important to us to keep all this card data safe. So classification from our point of view stems from our regulatory bodies like PCI SSC is like a global regulatory body basically. And card holder, they sort of tell us that the things that are sensitive is the card holder data, which is everything in front of your card, your PAN, your name, the expiration date, right? And then you have sensitive authentication data, which is your PIN, your CVV behind your card, and some track data like that. So these things are extremely high, the sensitive authentication data, and that's what we'll be focusing on, right? And I'll also touch on some technique that's very good for like the card holder data bit, but just as we go. And then like since we're using encryption, right? Your encryption keys immediately become as sensitive as the highest sensitive data, the data you're trying to protect, because any sort of compromise on that bit already compromises whatever you're trying to protect. So it's very important you treat your encryption keys as important as the sensitive data you're trying to protect. In fact, more important than that, to be fair. Um, so yeah, when coming down to data mapping, right? One good way to start is sort of to understand the flow in which data is going to go through your system. This is quite high level, to be fair, and it just basically shows how your data gets processed, your card transactions gets processed today. In case you didn't know, there are a couple players in between before you finally get debited when you put your card and you try to withdraw money. Um, so I've done the assessment, and then we found out that okay, the PIN data, right, is at rest in different places. Your card, your logs in any of the servers, any applications within our server, some storage device, especially like in the terminals that we use, and then databases, right? So all these things are listed are potential places we can store it. And why is it important to map potential, not just where you think you store it, is so you can be able to properly like put things in place to ensure that if something is not meant to be somewhere, they don't stay there. And yeah, so then we also have our encryption keys, possible places you can find encryption keys, probably some key store somewhere or in the code. Any encryption key in your code is bad practice. And this is why like I wanted to highlight that is some you see cases where this happens where simply because everything is protected, there's this firewall, the intrusion detection, this is your perimeter defenses are impenetrable. um every single thing you've done, all the way has been great. You're encrypting every single thing, but then you get to the code and you see the encryption key in the code stored in some Git repository, right? Social engineering is one very easy way to compromise any system, and all it takes is for someone randomly to see you coding and leave your laptop somewhere, and that's the end. They literally don't already know what's going on. So it's very important to highlight these places that are common and to put things in place to ensure that you do not compromise your system in any way. Um, and then data in transit is over some network. So let's go back to the requirements, right? So for a PIN, right, according to the standards that we have, right, the PIN should be irrecoverable. What does that mean? This means that your PIN should not be stored anywhere. Even if you are to encrypt it, right, you shouldn't store that. Your PIN should be unreadable. And by design, this is not really a requirement, but by design, your pins are sort of tamper proof. What do I mean? Um, if someone changes your pin from 1234 to 1233, the person cannot authorize any transaction because when you try to compare it, it will be wrong. So by design, it is tamper proof. Um, and yeah, and then we have encryption keys. Sort of the same thing applies to them. They shouldn't be readable. They should like the access should be very restricted, right? So that you do not, like I said, you do not compromise the keys in any like for any reason. Um, so when we were evaluating, right, this before we decided whether to use encryption or not, there's something else we could have used. This is called tokenization, and tokenization is basically an irreversible process of making like some text unreadable. So it's like example would be when you say anytime you see A, change it to B, right? The way it works is that you have some vaults that map certain sequences of characters to certain other characters. Whenever you see that, you replace it. Now, the vault itself is the only thing that knows what maps to what, right? And why I say it's irreversible is as long as someone has that token, they can't do anything with the token except pass it around. So the only person that could understand what that token is the vault and the person that is holding the cleverly in the first place. So tokenization is one way in that sense, meaning like compared to encryption, where encryption requires that both parties have the key, because the whole point is I should be able to reverse this. I'm encrypting this, so I'll give it to somebody, the person can reverse this and understand what it is that's behind that. So tokenization is great for putting things at rest in databases, right? So that anyone who sees it, right, has no understanding of what it's doing. Encryption is very good for things in transit. Why? Because you don't know what the person receiving this is going to do with that data. So it's best to allow the person to be able to reverse that, to be able to like perform some operation on that data, right? Um, so we chose encryption basically one priority, one reason being wide adoption, especially in the financial space. Adoption is quite key, even though tokenization is very, very strong in the sense, it offers very strong offerings. Like for instance, it's easy to rotate tokens, easy to invalidate tokens, just change the mapping. Compared to keys where you have to literally like regenerate and exchange keys. But today, integrating to many payment processors today, encryption is their de facto way of like integration, right? And also in terms of performance, right? Encryption is faster than tokenization. And if for financial transactions, right, we really care about the speed of transactions. So because I have a lot of nodes in the system, we try not to hold anything too long for any reason. It's easier to scale with encryption. Why? So you have like a database that maps to different like the token vaults, right? That you need to think about scalability. You need to think about redundancy. You need to think about a bunch of things like risk conditions, like all of those things, right? Um, it's difficult to scale that up and manage all of those things, although there are people who offer those services, right? Compared to a key encryption where you just give me a key and when you get this data, decrypt it and you're fine. So those are sort of the reason. Then less dependencies, right? To set up tokenization in like a financial space, right? You need the person that who's holding the clear data to be able to provide you some API that you can use to make sense of what's going on, right? And now if that API is down for some reason, like the entire system can't work. So like that's sort of like the reason why we chose like encryption end to end. Now for encryption to work great, I'll sort of walk you down the kind of things you should be thinking about if you're ever going to choose encryption to do any sort of thing. First of all, is to understand what technique you're going to be using. There's asymmetric versus symmetric types of encryption. Asymmetric basically means you have a key that encrypted it and another key to decrypt it. And symmetric means the same key that encrypted is going to be the same key that decrypted it. Now we use symmetric encryption because one is faster, two it's supported by a lot more legacy systems, and it works well with the hardware security module, which I'll introduce later on. So that's basically why we chose like symmetric encryption, and it also fits well into integrates well with a lot of systems because that's what most people use within the industry. So it's just a good fit for that. And then we go into the choice of algorithm. It's always best to choose an algorithm that's very difficult to break, and AES is one of like the industry standard because it's the best at the moment for as an encryption algorithm. And key management strategy. Now this is very, very key, very, very important when you are dealing with encryption. Extremely important. Um, and that generally five things you should think about that probably would be able to you need regularly is generating strong keys, storing keys, sharing keys, using these keys, and rotating these keys. Right. So in all of these things, right, we tried to figure out, okay, what could we use that is the best solution that enables us to be able to manage our keys in such a way that we can't compromise that. And then we introducing the hardware security models. Hardware security models, they are sort of like hardware devices, right, that are hardened, like they are tamper resistant. Like I say they have trust issues. That's just basically what it is. And we love them for their trust issues because it's built in such a way that it has like a master key, right, that it uses to encrypt anything that enters into it. And the way it is structured is such that if you try to tamper with the hardware in order to figure out what that thing is, it will self-destruct. I'm exaggerating, but it's going to basically delete all the keys and clear all the keys. So his job is to manage keys, encrypt, decrypt keys, and it's probably one of the highest, like most, when it comes in terms of like secure ways of managing and encrypting keys or managing keys. Yeah. So like it only ever gives out encrypted data, and it's the only one that knows what the clear data is. From the moment you put in clear data, everything subsequently after that is always going to be encrypted. So we chose the HSM as something to store our keys, right? So now, how does the HSM generate keys? It sort of uses like entropy sources. It can be like random feedback or noises that it converts into binary, and then it sort of like filters it or processes it to ensure that like there's no patterns, right? Because hackers are quite smart, right? And the second, the people have different ways for trying to figure out what is being done behind the scenes. And second, they can detect a pattern in something, they will just keep trying until they figure out something that works. So ensures there are no patterns there, cleans it up. And then a seed data is like a randomizer, is sort of extracted from that. And that seed data then is being used to in an AES algorithm with the local master key. That's the master, the base key that every HSM has, that's set once, and that's the end. So that's now applied to that to generate a key. Now, we apply multi-layer encryption, and a very good practice for multi-layer encryption is um, key encrypting keys. So what does that mean? It means the keys that if you want to use a key to sort of like encrypt a text, you should have a key that encrypts that key, especially if you are going to be transporting that key over a network. So the key we first generate is always a key encrypting key, and that key is what you share that key first with whoever the other party you're trying to share this sensitive data with. And in that case, it would be us trying to talk to maybe nibs or interswitch. And that's like we have to maintain this one key um, first of all. And they call it a zone master key. Why is it a zone master key? Any two parties, right, that are not within the same network, that are sharing like sensitive data, that are referred to as zones. And zone master key is your key encrypting key. And that's the first thing you guys have to sort of exchange with each other. Then subsequently, the key you actually use to encrypt the pins that you pass around is going to be, it's called his own pin key, and that stuff is going to be sent um, over the network at some other point. So um, yeah, so for storage, we already decided HSM. So sharing the keys. Now, this is very important, right? Being able to share keys between people, like there's a lot of trust issues with when it comes to key management, and rightly so. Something called the Shamir's secret sharing is sort of what's been applied. Doesn't always apply to this, can apply to anything. An example of that would be if you generate a password for something, and then you split the password into three different places, and you give each password to somebody else, and each person doesn't is not aware of the other password, the other piece of the password. Now those three people have to exchange that password individually with somebody else on the other side, and then they now put it into some system, and that system now brings the passwords together. This is sort of how Xiaomi secret sharing works, and you could apply to a bunch of things. So it's generally two ways. First, you have to find a way to split these keys, and then you have to find a way to share this or exchange these keys between two people or two or more people. And key splitting is quite so. The way it happens, key splitting is the same entropy data we spoke about. The HSM sort of generates two random numbers from it, and then it XORs it with the zone master key, and then you get a third component. Now, those three components are going to be given to three different people. Now, the way it works is like the HSM itself, like is guarded even like from like a perimeter point of view, like in a building. So someone's going to walk in, press enter, get this component, leave. Someone else is going to walk in, get that component, leave, and third person works in, get the component, they leave. Now, the yes, and then the next bit is to exchange it. Me, first time I heard this key exchange ceremony, I thought it was like an OML type thing. It was a very big delusion, but it's fine. Um, then basically what happens is, so like each person has a component, and you have to have a corresponding person on the other side that is going to receive this component and then load it back into the HSM. So the components itself, they're already encrypted, and when they load it back into the HSM is able to figure out what exactly it is that the master key is. but it will only return an encrypted version of that key. So in all this entire process, no one ever knows what the actual key is. And that's how key exchange works. And now using it, right, everyone has a key encrypted key. The zone pin key is the stuff that we use to encrypt the pin actually. This zone pin key is what is regularly rotated. So every single day, we're generating a new zone pin key and we're sharing it across each person. Now, the zone pin key, when it's coming in, is already encrypted with the zone master key. And just to know, like, HSM is the one that does all of this. No one actually knows what's going behind the scenes. You're just pressing commands, enter, and the guy just knows, okay, I know what this master key is, and I know how to decrypt it, and I know how to apply it. And then what the other zone is expecting is this. I'm sending you a key that is encrypted. I need you to decrypt the key with the master key I shared with you before. You're going to get a clear version of this key, and I need to encrypt this text with that clear version of this key. When this text comes over to me, I'm going to try and decrypt it with the clear version of the key I just sent to you. If it doesn't work, I'm going to deny this transaction. So you see there are a lot of multiple layers of security that applies here in such a way that at any point in time it's very, very difficult for you to even understand whatever this key is, what this key is, or even able to compromise like what text is going over the air, right? Um, let's see how that happens, like side by side. So earlier I mentioned tokenization and encryption. I would always advise to use both of them in your systems, right? But for card pin, right, there are different times where you don't have to use both of them. An example would be um, in like handling pins, right? So when you're processing like transactions in terminals, there's something called a pin block. That's actually what is being passed around. Your pin is never passed, it's your pin block. And the pin block is generated by some encryption also. So if you're using an ISO format 4, which is like a very recent format, right, you don't need to tokenize the pin block. Why? Because every card has like a mini OS on it, and the card has like its own keys. And the only person that knows those keys are the person that issued you the card. That's the bank. If you're using a UBA card, the UBA knows the keys. Now the terminal will forward your PIN where you entered to the card. The card is going to encrypt the PIN with the key that only the issuer knows, get an intermediate block, and then it's going to XOR that thing with your PAN. That's the numbers on your card. And then you get an intermediate block again. Then it encrypts that intermediate block, and then you now have your PIN block. Because of this reason, right, even if you know the pin that's being sent, like the pin block that is being sent from your terminals, you can never know what the clear version is. So like you don't need to tokenize in that sense. But there's an earlier version of ISO format 1 that can be reverse engineered, because the way it's generated is just a very simple Excel statement. So in that kind of format, people tend to tokenize that before sending it, right? Or they encrypt it again with some other keys before sending it. So that's sort of how like it works in terms of the multiple layers of encryptions we have when we are trying to handle your card data. And in doing all of these things, right, even this pin block, for instance, even if you log the pin block to your logs, for instance, no one's ever going to understand what that thing means. And when we communicate like terminals, right, we always ensure it's over some secure protocol. TLS 1.3, that's what we use. And then we have like client server authentication to ensure that only our terminals can actually talk to our servers. Um, so then or I wanted to pinpoint something called pin translation. This is just like the flow through the system, right? I mentioned now that we don't log things to the database. So like we have like a library that ensures that we always keep things sensitive. So because this comes in like ISO message format, we know the fields that contain sensitive information. So those sensitive information, we can decide whether they're able to write it to a console, or whether you can write it to logs, or whether you can log it to the database, right? It generally would decide all of those things. So we have that already built in. And what I want to talk about here is pin translation. Pin translation is between two zones, they should have a unique key. That's the general rule. So my terminal talking to my backend server, we both share one key. And me talking to a payment processor, we share a different key. So it means when a pin block is coming from my terminal to me, it is encrypted with a key that only me and my terminal understand. I need to translate that pin block to something that me and the processor can understand. That's what's called pin translation. So you're taking an encrypted value that was encrypted in a key that is understood between one zone, and then translating it to another value that can be understood between you and other zone. So yeah, and the HSM is like a major player in all of these things, right? HSM is actually a physical device resident somewhere on site. But what we do is we build a proxy. I can show you here. There's a proxy at the top right that forwards requests to HSM on site and run this command for us. And then we have like we're able to see like the encrypted data and all of those things. No, we're able to get encrypted data and be able to translate pins. And it's tailored for payments, right? Which means we run specific commands for pins, right? HSM is generic normally, but you can say I want to specifically run this. So yeah, so like that's sort of like the setup that we have. And then from this, we have like micro segmentations of subnets that we sort of put internally to prevent something called lateral movements, right? Lateral movements is saying this: ideally, if you're within the same network, you generally trust each other. So lateral movement is ability to move within the same network. It's always advisable to not allow that freedom, right? Because if one network is compromised, it makes it easy for you to compromise every other network in the system. And I'll sort of talk on something that's very important in solving that kind of problem. So I mentioned earlier about the transaction handling library we have that is very context aware. It's aware of the environment you're in, it's aware of the log, the way you're the way you're writing certain things to, so that it's easy for you to enforce readability and recoverability at different levels. Um, yeah, and then defense in depth. Like this is sort of like a broader strategy that is applied. Everyone should think about it this way. Perimeter defense being securing the boundary of your systems, and a lot of people are very used to doing this in personal firewall, intrusion detection systems, right? But this alone cannot be sufficient because the second someone is able to break into, especially internal compromises, right? Having very micro segmentation and fine grained access control to every single subnet is essential to keeping things secure and ensuring that like the compromise on one side doesn't spread out. Yeah, then I already spoke on multi-layered encryption. Now, what I wanted to mention as an honorable mention is zero trust architecture. Zero trust architecture, like I said, is one of these things that has a very big trust, like has trust issues. It's basically saying I'm encouraging you to have trust issues. I'm encouraging you to not trust anybody, even if you guys are in the same network. Like even if you guys are in the same compound, even if you guys are in the same room, you build things in such a way that you don't trust each other, and it's designed to limit internal lateral movement. So an example can be enforcing maker checkers. So I want to generate a token. I have a port that I can call to generate a token. This server can call me to generate a token, but this server cannot call me to generate a token because I have NSG network security rules set up in place to ensure that I minimize that particular interaction. So those like zero trust architecture is something that I would say like everyone's sort of looking deeper into and understand how that can apply because the principles are quite great for securing like systems. Right? If you do things knowing fully well they're not going to trust any other person, then it's easier for you to always stay secure um, at all um, at all times. So I think that's pretty much everything. Right. To wrap up, like is if you're going to be considering encryption, right, I think you should factor in multi-layer encryptions so that it reduces your attack surface area. It makes it difficult for people to eventually get to what they're trying to look for. And it also protects you internally because social engineering, like I said, is one key thing that's always like is one of the easiest ways to disrupt any system. You can set up the best of the best perimeter defenses or encryption systems, right? And the login, you find someone that has like login credentials, right? And you just know the person's login credentials. That's pretty much the end of everything you just set up because now I have authorized access to your systems. So, um, yeah, so that's why it's very important to have those things like nested and layered to the point where it's difficult to even understand what's going on. And so I sort of had like an exercise for everyone that we could try at some other point. It's something called like jungle language. I'm pretty you might have like you might have come across it in like secondary school or something, where we replace alphabets with um numbers. So A I O U replace it with numbers. Um so it's sort of run like a tokenize a particular thing that you've learned in this conference so far. It could be in this talk, it could be some other talk, and at the speaker, sys design, sys conference, and hashtag conf gym, and then sort of put the tokenized version of whatever you learned, and share it, right? And see like if people can figure out what that is, just by looking at it. Yeah, and see, thank you very much for listening. Have a good day, I guess.
Thanks, Toby. We have a few questions if you have time.
Sure.
So there are like three questions. I think we can get through them.
All
So
right.
the question is, how do you handle detecting when a compromise happens? E.g., if a pin gets logged by mistake.
Yeah. So the key thing is a pin gets logged by mistake. How do you handle already logging it? Like I was saying, it's also already logged in the, you can already see it put in the logs. First of all, I would say you need to walk back to understand like the thing that caused that in the first place, and is to solve that problem first. If you are logging clear pin, it means that you are passing clear stuff in the first place. So you can either tokenize it, that's if you intend to actually, if you are meant to store it. So you can either tokenize it or you encrypt it from the entry point. So that's why key. Your edge at the edge, right? So when someone types in, let's say your pin is 0000, before you send it into your system in the first place, you make sure it's encrypted. So that way, even if you log it, right, there's no compromise. Like if you're already doing that, you need to sort of solve that problem, or you can intercept your request and tokenize them before sending it to your services. So like that's sort of how I would like navigate if you've already done that. Um,
Yeah, but
and
like, what if let's say you haven't set this up properly, right? Like there was no prevention, and there's a compromise already. Like, how does, I guess the question is, how does your system like detect those kind of circumstances? Is it like people report, or like you have a flag or something for?
okay. So the way ISO messages work, and this is specific to ISO messages, though. Your logs, for instance, all these places where data is at rest, they are continuously audited, right? So in ISO messages, right, sensitive data is always in a particular field. So it's like every single time we're auditing the logs, we're checking if that field contains a readable data. So if you have logged stuff right now, you can set up things to sort of go through the logs, like can be um, any sort of like log management system that you're using today. So those audits are the kind of ways we sort of tell like that something has happened. The other way, which is the worst possible way, is if someone comes and reports that there's an issue, and then you start reporting, you start investigating, and then you figure out there's a problem. So I think those are like the two things that I know that like we'll do auditing, periodic auditing to sort of figure out what that is. Yeah, I think that's and then like once you found that out, is to fix it immediately. Like I said, this is extremely sensitive data. It's not a thing for you to put off to later. It's something you need to sort out now.
Okay, thank you. Next question. Is tokenization mapping one character to a single tokenized character, or is it like hashing? If yes,
So okay. So tokenization is like you well, it's not hashing. It's not hashing. In a way, they are similar, but tokenization isn't hashing. Yes, it's literally saying that this particular sequence, it could be a sequence, it doesn't have to be a character. It could be one character, it could be a sequence of characters. You're saying that I'm going to map this character to this particular thing, right? That is what tokenization is, as opposed to hashing, right? So tokenization can have some semblance to the original text, right, in the way it is mapped. So it's not hashing in that sense, right? It's just you mapping that. However, what you want to map that thing to, you can hash it. That's really up to you. So you can decide that one is mapped to the hash of 5, and 2 is mapped to the hash of 7. And anytime you see 1, 2, you replace it in that sense.
okay. And then what about offline pins? That is the data at rest? If yes, how is it secure?
Okay, yes. Actually, offline pins data is at rest, right? So the way the thing works, like I said, cards have chips in them, and those chips are like mini OSs. So every card has its own mini HSM. Every card has its own mini OS. So when your issuer, when you create a card, and issuer creates these cards for you, and before they give it to you, the when you sort of, what's it called, when they register your card or something like that, they write your pin to the card, right? So offline pins the data is at rest in the system in the card, in the HSM in that card. So when you type in your PIN, the terminal pushes that PIN to the card. The HSM sort of encrypts your PIN and compares it to see if they are the same thing. So it is at rest in the card, but the chips are created in such a way that it has an HSM inside the chip itself and an OS inside the chip itself that sort of validates that for you. So yeah.
Okay. Yeah. Perfect. Thank you. I think that covers it. Someone's asking for slides.
Okay.
I guess we would coordinate with you to share slides. But thank you so much for coming up to talk. This was fun.
All right,
Uh,
man.
hope to see you at the next conf.
All right. Take care, man. Sure. Bye, guys.